Here is another dimensioning system. This is rectangular coordinate dimensioning using tabulated dimensions. Okay, in which case we have a series of holes here. Holes A1, A2, B1, B2, C1, and C2. They have different sizes and they also have different locations. Okay, so the sizes, excuse me, the sizes of the holes are given in the table. The tolerance of the holes are given in the table as well, and the x and y location based on 0, 0 being this corner is given in the table. This is another valid way to dimension a series of holes by using tabular dimensions. Another dimensioning scheme is the polar coordinate dimensioning. So it includes angular dimensions. So to define like this whole location correctly, you would need to give it both a radius from the center point and an angular dimension, okay, to define, what the position of that hole is. That is the polar coordinate dimensioning. Now dimensioning parts on a drawing, if you've been through this with working drawings too, and it's just, well, you need to put a dimension on every feature. And one of the things that the author says to help you do that is to mentally break down the parts into the shapes that form it. I mean, obviously, if you're working in 3D CAD, you do that anyhow. I mean, you develop a block, you extrude a block off of it, and then you'd make a cut here to cut it off, and then you generate these holes. Each one is a feature, and each one requires a dimension. So, all of these features that you see here will have a dimension shown over here on this. Okay, so it's just a way of making sure that you get everything dimensioned properly. Um, Here's a good tip. Dimensions applied where contour of feature is best shown. Okay. Um, for instance, this 1.5 inch dimension, it shows that this is clearly an angled surface off of this part. Okay, if we tried to dimension that 1.5 inch dimension, say in this view down here, for instance, it's not giving us the clearest picture that we could get. By putting that dimension up here um, and attaching it to this view, this upper view, then that's where you get the best representation of it. If you notice what they're doing here, this is something we talk about dimensioning between the views here. So we got a view, and dimensioning in between it. Um, that's this topic of the next slide. Size and location dimensions placed between views when practical. Do not place dimension between views if extension lines run across several features within the part. You don't want to do that, but it is best to place your dimensions between the views. It's more clear. Um, Dimensioning outside the geometry. Extension lines long enough so dimensions appear off the part. In any saved or orthographic views, extension lines extend features outside the object to allow placement of dimension lines. So that's what extension lines are for, and you want to be dimensioning off the object of the part. Now the next slide talks about dimensioning according to related features. If you go look at the example of this in your textbook, what they talk about, and it's right here next to this figure 327, is that we have this angle bracket right here, and then we also have this block. This block here includes a latching hole that works with this solenoid. So when you look at the dimensioning scheme of this bracket, it shows a dimension from this lower surface where it mounts to the hole here where the solenoid mounts through the bracket. Okay, and then that would be the same dimension that the designer is going to place on this slide block from the surface where it meets that same plate up to, I think in the example in the textbook, it says that dimension's 0.438 inches. Okay, so you would dimension those the same nominal dimension, but minding the tolerances to make sure that it lines up properly. Okay, so the parts must function together, and then that's part of your cues to figure out what dimensions to put on parts. If this solenoid has to align with the latching hole in the bracket, you got to dimension it accordingly. This slide's on the general arrangement of dimensions, and it's kind of a sin to cross extension lines and dimension lines. So you want to avoid crossing extension and dimension lines. So therefore the larger dimensions typically go on the outside, so the smaller dimensions are closer to the part, and then the larger dimensions go farther away from the smaller dimensions. In that respect, we keep from crossing extension and dimension lines. Staggered dimension values. Yeah, dimension values on a single annotation plane must not overlap in the model. Staggering clearly shows values when multiple rows of dimensions. Staggering dimensions definitely helps. See your textbook for a example of that. And here's a little bit about how to dimension hidden features. Dimensions may be applied to internal features in models. That's kind of why you would use hidden features. If you take a section view, yeah, you need to show. That's the reason why you would take a section view sometimes, is just to be able to show features that you can't see from the regular orthographic projections. Okay, here's the point on double dimensioning. Okay, so this is what was in the other lesson too, but we have this part where we've got these 4 dimensions. Well, one of them needs to be basic. I mean, if you're controlling 3 of these dimensions with tolerances, the other one you can't control with a tolerance, because you need to allow that one to float a little bit. So we fix this condition by placing a reference dimension on one of the features. And once we do that, it's not considered double dimensioning. Okay, this is considered double dimensioning, but this one over here, where we put the reference dimension, is not double dimensioning. Here's how to use the origin symbol. Well, it's kind of like the arrow, but what we're doing is we're designating that this lower surface is where that dimension orients. It's kind of dictating that when you inspect the part, you need to hold it flat against the surface plate, a granite surface plate or something, and then be able to measure that from that feature. Essentially, the origin symbol replaces the arrowhead. This slide talks about auxiliary views, and you use auxiliary views so you can show the true shape of features on inclined or oblique surfaces. Okay, in this case we have an angled surface right here, and we want to look at what the dimensions are of everything on that face. We take an auxiliary view that shows us that face in the inclined view. Here's a little bit about dimensioning a section view. Section lines create need for special consideration when dimensioning. They're drawn with the same thin line type as extension lines. And then just industry practice here sometimes breaks section linings around arrowheads. Okay, see what we've done here? Yeah, and then sometimes you break section lines around extension lines as well. So that's what's being done there. So, dimensioning orthographic views. Dimensions on 2D drawing planes despite 3D drawing view axes, used alone or in combination with orthographic views. Okay, notes used in dimensioning. So information that cannot be clearly shown through the model or geometry, you want to use notes. Okay, specific notes, leader is pointing to something with the note shown locally on the field of the drawing, or in some cases you could put the leader with a note number, like a flag number at the end of the leader, and then in the drawing notes section on your drawing, you would put a drawing flag with that same number in it, and you would say what the drawing note is. Now, contrast that to general notes, where general notes apply to the entire drawing. And then you can have another note that would say, hey, see separate notes list, or see separate parts lists, or a note indicating the existence of the separate parts list. In some cases, the parts list exists in another system, and you wouldn't have that available on your 2D drawing. So I'm going to end this movie here. Thank you.